Good afternoon, ladies and gentlemen of Algebra 2 Honors. Good to have everybody back here today. Everybody's back here in apparently good health. That's what it looks like to me, or that's what I hope anyway. All right. Problem 7. Write the function represented by a graph and state the domain and range using set notation. So basically, our parent function for this is going to be f of x is equal to ab to the x minus h plus k. And what can we put in for these values here already? K is equal to 1.
K is equal to 1.
Anything else? Yeah, h is equal to -2, and I'm going to explain how we got that. This point right here is the one this is transformed from, okay, so I'll put from 0, 1, right? And so that means that to get transformed from 0, 1, we had to move 2 units to the left, therefore h is equal to -2. And so that being the case, we can write what we have so far. F of x is equal to a times b to the x plus 2, and then we put over here plus 1. Questions on this so far? Okay. So what's the next step we're going to make on this? Plug in some numbers, exactly. So we're going to plug in this one right here. And so we're going to have 5/3 is equal to a times b to the x, which is -2, thank you, plus 2. And then over here we put plus 1. What's -2 plus 2? 0, right? So we have b to the 0 power. So what we've done is we have the right number to reduce all this to 1. So we have 5/3 equals a plus 1. How many thirds do we have in 1? 3/3 equals a plus 3/3. So we can subtract, what's 5/3 minus 3/3? So a is equal to 2/3. So now what we have is we have f of x equals 2/3 times b to the power of x plus 2 plus 1. And now what can we do? We take our second reference point right here, and so I'm going to put here on the left. We have -3, or excuse me, 3, right? I put -3. I meant to put 3, didn't I? So 3 equals 2/3 b to the power of now -3 plus 2. And then put plus 1 over here. What now? How about subtract the 1, right? If we subtract the 1, we get 2 is equal to 2 over 3 times b to the -1 power. I'm just going to come to the right here. So we can rewrite this as 2 equals 2 over 3b. Why do we put 3b? Why do we put b down here? Yeah, b to the -1. So b to the -1 in the numerator becomes b to the 1 in that denominator. So now you can cross multiply the b and divide by 2, so b is equal to 2 over 2 times 3. which equals 1/3. Right, that cancels out, equals 1/3. So we have our equation now, which is f of x equals 2/3 times 1/3 to the power of x plus 2, and put plus 1 over here. And then you can test in your calculator and see if it lines up those reference points, right? And the last thing, it says domain and range using set notation. So domain is going to be x such that x is element of all real numbers, and range y such that y is greater than 1. Okay, so we got our domain and range, we have our function, we have things looking the way we want them, right? Okay, ready? Everybody ready to move on to number 7? Or number 8, excuse me. Number 8. Okay, number 8. Given the exponential function f of t equals 3 times 0.5 to the t power t, find the average rate of change from x equals 0 to x equals 6. Does anybody remember first semester about average rate of change?
A little bit.
A little bit? Yeah, it was a while ago. I'll give you that.
Honestly, he's pretty good at that.
Yeah, I'm sure he is, but I'm sure you're even better.
Oh, wait.
So what I want you to do, Peyton, is tell me what it is.
It's this thing in math where you take numbers and letters and you...
Really good. Okay, I want to give you the formula.
This slope, this y equals an x plus 3.
Okay, that's exactly right. That's exactly right, Connor. Connor, you're exactly right. I'm going to explain why Connor's exactly right in a minute. Okay, you and Connor. You guys. No, I'll show you what it is, because really it's good.
I'll just turn around.
Okay, Connor's so right, he doesn't even know how right he is.
Yeah, Connor, can you show us how to do it?
No, I'll show you. Connor, that's okay.
Mr. G wants to.
Okay, AROC, which is an acronym for average rate of change, is equal to f of b minus f of a over b minus a. And what this is just kind of a function notation version of the slope formula.
Yeah, this is what, that.
So that's why Connor is exactly right, because it's just a different version of the same thing. So what we're doing here is we're saying that we're going from A to B, and so A is designated by convention as lowest value. So here we have A is equal to 0 and B is equal to 6. So what this means is, in this case, we have f of 6, which is f of b, minus f of 0 over b minus a, which is 6 minus 0. So really all that's left for us to do now is to find out what these are. Well, f of 0, if we plug in 0 to this, what are we going to get? We'll get 3 times 0.85 to the power of 0, and that's going to be what? It's going to be 3. So it's going to be equal to, we have minus 3 over here in the place of f of 0. And f of 6 is going to be 3 times 0.85 to the power of 6, which equals, you can go to your calculator, and it's going to be 3 times 0.85 to the power of 6. So we get 1.1314, we'll say, right? And so what we get here is 1.1314 minus 3 over 6. And so we can put that in the calculator, and what I'm going to do is I'm going to use the stored value for f of 6. So I put second ANS, and I'm going to subtract out 3 and divide that by 6. So we get negative 0.3114. So that's what it's going to be. Okay, I appreciate Connor remembering for somehow he did it, that this is analogous.
Connor knew.
That is analogous to the, yeah, he did, so he put on the spot.
No wizard.
He's out playing baseball.
I think Connor watches the videos under a different YouTube account.
He does. He's skinny.
Any questions on this one? This is not that bad, is it? Okay. Let's go to number 9. Now, number 9 is something, really, it introduces something we haven't covered in this class yet. In chapter 13, there are 4 sections. 13.1 has to do with geometric series and sequences. 13.2 is exponential growth. We did that one quite a lot. 13.3 is exponential decay, and 13.4 is the exponent, the function base e. So it's going to be f of x equals e to the power of x. That's our parent function. And so we're going to talk about what e is. E is something called Euler's number. Yeah, so Euler was actually, I believe, a Swiss mathematician. But he's Swiss-German, right? Switzerland is kind of broken up into French-Swiss, German-Swiss, Italian-Swiss.
Yeah.
So he's a German-Swiss guy. Really smart German. And it's kind of a number that's named in his honor. And it's a number that has special properties that are helpful in finance and in growth and in calculus. It's approximately equal to 2.7128.
8282.
right? Something like that. So 1.8282.
Yeah, that first 2 is not there.
Okay. Thank you.
This is 0.71.
About that.
This one right
He said the
here.
first 2.
I think I did. I said it. So anyway, but this is it.
You're right.
And in your calculator, I want to show you where that is in the calculator. Okay, the calculator you get by pressing second and your division sign, and then you get it right here.
Second division sign. Oh yeah.
Yeah. Okay. So that's where it's from. So just in what it is, we're now probably ready to tackle this problem. The town of Silver Springs has its population of 5,000 at the beginning of 1990, and it grows at exponential rate to 12,000 at the beginning of 2020. The exponential growth function models this situation. It says if, it's supposed to say is, okay, is this right here, where P sub 0 is the initial population after 1990, and P of T is the population of time T. Determine after what year the population will be 20,000. What is the growth rate of the function? Well, we're going to answer that last question first. What is the growth rate of the function? Well, R, now the basic parent function is this, P sub 0 or P, excuse me, A of T, I'm gonna put A of T. A of T is equal to P sub 0 E to the RT. Okay, R is the rate, and in this case the rate is 0.029182. Or, alternatively, you can write this as 2.9128, 2.9182, 82%. All right, so that would be what R is, or what rate is. And then what is determined the population, when the population will be 20,000? Well, here you can enter these equations under Y1 equals 5,000 E to the point 0.029182 X and Y2 equals 20,000. All right? And in your calculator, this is what these functions look like. Kim, do you have a calculator?
Yeah.
Yeah, you have a calculator? I'm telling her that because it's a little bit helpful now, but especially will be for what we're going to do next after this. And so we graph. When you graph, in the window, I'll show you the window I set that was like this. I don't know if that's helpful to you, but that's the window that I set for it. And when you're actually working the problems right, you're going to be able to experiment yourself and find the right windows. Is that right, Abby? You need to do that?
Hopefully.
Hopefully, she says.
Yeah, mine says error.
Yeah, let's go to function. And it says error, Addie?
Mine does too.
Does it? It's not. So we'll just have to fix what that is, whatever it is. We'll be able to fix it.
It is.
It's a straight line.
Oh, type of X.
Well, your error is the window.
Okay.
The problem you have is Y min is bigger than Y max, so it does not.
So close, it almost
So
goes
it's
straight.
because it says error with middle range, so now you
Several times. Kidding.
Oh, I didn't enter that 1,000.
Yeah, also need to put X up here.
Oh.
No, it doesn't say error. It says error. Here it goes to X trace.
X.
Does he not?
And then put 20,000 down here.
Then
Then you should have this point. Yeah.
I was signing.
Okay, you need to put X and.
Yeah.
Okay, is everybody good with this now?
Oh, no, there's error.
Now this is the formula for, do you see over here in financial math, that formula's up there over by Peyton? Okay, it's a formula for continuous compounding. So interest, when you have a interest-bearing account, now in 21st century, will usually compound continuously. Why do we do that in the 21st century as opposed to the 20th century?
Because now we have more money.
Well, now we have more calculation capacity, because it's something that takes more calculation horsepower than was easily available, in especially early 20th century. Okay, so now we go and graph, and you find the intersection point, second trace, 5, enter, enter, enter. So 47.505. So x 47.505 years, and then it's asking the question, determine after what year the population will be 20,000. So this is going to be 1990 plus whatever that figure is. So 2023.505, right? 2037.505, is that right?
Where'd you do that, Mr. Joe?
Somehow that number doesn't look right, though. Where did I get A and S from? Because that's the right one.
You're right, that it's gonna be.
Yeah.
Because it picked the right one, that's right, because it's 14, but see, it didn't pick.
If you just do
That's also-
E plus
Yeah.
1990, you get 1992.
Yeah,
0.718.
See, I don't know,
Adding on to the other ones.
because it should have added to that other one. Anyway, whatever. But it should be 0.585, right? I guess somehow the calculator knows that. That's the right answer, by the way.
It's up where.
So that's the right answer. So during, it says after what year? So after start of 2037, right? Actually, about halfway through the year, right?
Oh, we're using that number? I thought we were using 1992.
Yeah. Would you get 1992? That's what I got.
0.718282.
No, because look, it's going to be, you got to add this one right here. So this is how many years after 1990. So 47.505. 0.505 plus 1990,
Oh, okay.
right?
Yes, but, so you don't do 1990 plus E?
No, it's 1990 plus, it's 1990 plus,
47.
plus this number right here. 1990 plus this.
So after the start of 2037?
Yeah, after 2037. Okay, so that's going to be it. So hold on to your packet. We're going to be working on some, starting on logarithms today.
Oh yeah, because we have a test tomorrow, right?
Yeah, we'll have a test tomorrow, that's right. But we're going to talk about
I just put.
start talking about properties of logarithms. So it starts out with the essential question, what are the properties of logarithms? And then it says, in the teak there, it says rewrite exponential equations as corresponding logarithmic equations, and logarithmic equations as their corresponding exponential equations. And so knowing how to switch between the different types of equations is going to be helpful for us to solve for an unknown. That's what it amounts to. So the first thing we're going to do is an exercise to investigate the properties of logarithms. So this is an exercise in your calculator. Alright. So you have, I want to show you where some of the keys are for this. We've already checked out the E key, right? So we have the log of 10 over E. So we go here and put the log, here's the log, where that is, of 10 over E. And E, as I hope you recall, is second division sign. So that's where that is. So we get 0.5657 about. So we put 0.5657. And the next thing we have is ln 10. Now what does ln stand for?
Oh, it's ln.
Yeah, it's ln. It stands for Logarithme naturel. That's why I call it ln instead of nl. That's French, from the French. Logarithme naturel, that's what they call it. So it's ln 10. So ln right here, and what that is, that's log base E. ln 10, we get 2.3026. And then we have log e to the 10th power. So you go here and put log e to the power of 10. Whoops, I meant to go ahead and put like this, 4.3429. And the last one here is log 10e. So log 10e. So we get 1.4343. 1.4343. Okay, what I want you to do is work on this set B to the right and just see what you get. Just check those numbers. So it's really kind of an exploration, learn by entering in the calculator, seeing what you get. Okay, what are you getting for in set B here? What's 1 over log E?
2.3026.
Okay, so 2.3026. 1 plus log E, I'm going to guess that's going to be 1.4343, is that right?
Yeah.
1 minus log E, that's going to be 0.5, right? Okay, and the last one, by process of elimination, is going to be 4.3429. And so what this is kind of a backdoor way of looking at some of the principles of logarithms. So just for example, this last one here, this log 10e is equal to the log of 10, which means log base 10 of 10, plus the log of e. Well, according to property of logarithms, this log base 10 of 10 is equal to 1. So that's going to be 1 plus log base e, or log of e, which gives you this one right here. So they're varied properties, and similarly, this 1 minus log e is going to be this one right up here, because you're dividing. Okay, this one here, this log e to the 10th power, what you do is this 10 comes out front. When you have the log of something to the power of something, this 10 is going to come right out here, and you're going to get this one right here. Okay? So just some properties, and we're going to, let's see what this one is, this 2 point. Yeah, 1 over log E. Yeah, ln is the log base. I'm trying to think of how they got that. So log base E to the power of 10.
Was it?
Equals log 10 over log E, and log 10 is 1. So that's how we got there. Okay. What I'm going to do is get you to a table that I want you to take notes on here. This one right here, properties of logarithms. So I want you to write this down. And we're going to, on Wednesday, really start hitting this pretty hard about going over some exercises with properties of logarithms. Now, some of these things we've already done a little bit through that exploratory exercise where I had you enter those things in the calculator. While you're writing this down, I got a teacher appreciation token from Elizabeth. You know Elizabeth?
Oh, yeah. Yeah, remember her name's a...
Yeah, she's an artist.
Spelled with an E and everything, Elizabeth.
Yeah.
And a B.
So she said, I don't know if she said, Mr. Jerome, it's Teacher Appreciation Week. I want to take a moment to tell you that you are a great teacher and that we appreciate everything you do. Your class is always fun, and we love hearing the songs you play on the guitar. Thank you, Mr. G. Happy Teacher Appreciation Week. Now, isn't that really a nice thing to say?
Yeah.
That was really nice. And what's going to happen, you guys taking pre-calculus next year, which I hope are most of you. We have a pre-calculus song that's about unit circle trigonometry. Yes, sir.
They comment in it, man. Thank you. Comment in it. Here, I got it. Comment. Okay. We got been selected by
And did others of you get these before too? Probably some of you
Yeah.
did already, right?
What are those?
Did you write this down?
Wait. Teachers had checked. Wait,
So we have a couple people still writing down on this.
What are we supposed to write? The table.
Yeah, all the table. All of this.
Selected by the
Okay.
to receive an award.
And here's another thing, is that there's the award ceremony next is what, the 11th is what day of the week?
Tuesday.
Tuesday, right? Well, we're going to have our own award ceremony the day after, our own class awards. We have a class award ceremony too.
Also.
Because what happens is not everybody, because the awards that I gave is not to everybody. I was limited in the number of awards I could give at the banquet, is what I'm saying. I have some other awards for the class.
Will there be cookies?
I wasn't planning on that, but maybe later on in the week, we'll say, next week.
Salsa?
Maybe, because that's one thing I can make. Okay, I can make that. I can make chili too. The chili.
You know what was really good, what you did, that dip you made?
Oh, the dip, yeah, I
That
can
was-
make that.
that was
What dip are y'all
good.
talking about?
Yeah, you did dip.
I wasn't here for it. I
You
guess.
see?
You missed out.
Let that be a lesson to you. You gotta come to class. Forget about those cows and horses. Come to class.
Forget about them animals, man.
Hey, you know,
Come get some dip.
Hey, you know,
Okay, class is still in session. Class is still in session. There's very little left. Well, we'll see about that, since you mentioned that dip. We'll see about that, maybe. That's what we'll work out, because it's kind of,
Do we have more right now?
I do have a lot of appreciation for this class, and I'll tell you about, I've told you before. Let's go ahead and work out this one. Your turn. Express each expression as a simple logarithm, as simplify as possible. Well, using the properties of logarithm, we have log base 4 of 64 to the power of 3. We can take this 3 using the power property. So we have 3 log base 4. And can we rewrite 64 as a power of 4?
Yeah.
64 is 4 to what power? It's 4 to the third power. So what we have is we can take this 3 and multiply it by that 3, so we get 9 log base 4 of 4. And what's log base 4 of 4? It's, look at the properties of logarithms. Log base, we're going to see log base b of b equals 1. So log, it's the same number, it's 1. Because what this is, it's the power you raise 4 to equal 4. So our answer to this one simplified is 9. So that is our simplified answer to that one. Okay? And now this one here, for this next one, 5, we have this going to be equal to log base 8 of 18 divided by 2. So that's the quotient property of logarithms. And so that's going to be simplified to log base 8. Let me write the base better. When you write that, you want to write the 8 kind of as a subscript. And then you have 9, and 9 you can write as 3 to the power of 2. So that's going to be equal to 2 log of base 8 of 3. And then if you wanted to write that using a change of base formula, you could do that too. That's going to be equal to 2 log 3 over log 8. You could do that too. And put that in a calculator again. Anyway, that's some manipulations you can do with logarithms. We're going to do some exercise on those on Wednesday. But that's really as far as I want to go today.
So number 4 equals 9?
It's 9, yeah. It's 9, that's it. Yep. And